Now another capability of this instrument is what we call clock mode, and I'll show you how that works right here. So the red trace on the oscilloscope is just the photodiode output. So that's the difference of those two photodiodes, and this signal is proportional to the position angle of the torsional oscillator. So there it is oscillating away. Now inside the electronics in this chassis, we condition that signal a bit. We take this curve, the sine wave, and first compare it with 0 and turn it into a square wave, and then take the derivative of that signal to produce this yellow curve. Okay, and that's the voltage which comes out of the chassis here, and what we call a clock drive out. And then we take that pulsed signal, which is derived from the oscillations themselves. We take the pulse signal and feed it back into the drive coil. So now the oscillations are being fed back in to sustain them. So it's a self-sustaining oscillator. Okay? And we call this clock mode because this is essentially how all clocks work. There's feedback from the oscillations that produces some kind of a drive which gives the oscillator a kick every now and then. In this case, it gets a kick every half cycle. Okay? So now it's running in clock mode, so that the signal generated is not doing anything anymore. It's disconnected, so it's entirely self-sustained. Okay? And now one can measure the frequency of those oscillations. You can measure it using the scope, for example, using the measure mode, and you'll find that it's equal to the resonant frequency of the oscillator by all the other means we can measure it. Students are always a little surprised by that. They think if you're kicking the oscillator with something like this, that maybe the frequency changes. And in general, that's true. The oscillation frequency, the resonant frequency of the oscillator will change depending on how you're driving it. And in general, the resonant frequency will be a little different when you drive it as compared to the natural resonance frequency of the oscillator. But the difference goes like 1 over Q squared. So with a high Q oscillator, Q over 100, the difference is a part in 10 to the 4. And that's really unmeasurable with this instrument, or rather it's measurable, but it's beyond the stability of the oscillator itself. And so for all intents and purposes, all the resonance frequencies are the same. It doesn't matter much how we drive this oscillator, the resonance frequency is unchanged. And that greatly simplifies the mathematics. If you look at the math of driving an oscillator, the resonant frequency will depend on how you drive it, but we don't have to worry about that because to the order of magnitude we're dealing with, all those frequencies are the same. And that makes, like I say, greatly simplifies the math, and that's a wonderful thing to have in the lab, so students very much appreciate it. So like I said, you can measure the oscillation frequency using the oscilloscope, the measure feature, or another way, which I kind of like, is we use this very precise clock we have in terms of this function generator. So here we have a function generator now producing a square wave. That square wave is not used for anything, it's just going into the oscilloscope. And there's the clock drive signal. Okay? So now what we can do is just change the frequency of the signal generator, and you'll see that this will start to drift. Okay, let's change it by a bit more here. Give you something to look at. So there it drifts. And that's, of course, the drift rate is just the difference frequency between the natural mode, the resonance frequency of the oscillator, and the frequency that I'm driving the signal generator. And so I can adjust those to make them the same, or close to the same, and until one does not drift. Okay, and I can blow this up on the scope, like so, and really make this quite precise. So now I can just try to make that red trace not move, and I can sort of be a human phase lock loop here. I'll watch that, and when it moves to the left, I'll just change the frequency a bit. When it moves to the right, I'll change the frequency, and you can make a very accurate measurement of the resonant frequency of the oscillator this way, easily to a millihertz. So a part in 40,000. Okay. And one thing I like to have the students do is make that measurement, write down the number, and then you just blow in here a little bit, blow on those wires ever so briefly, and that will heat them up, and you can easily change that frequency by a couple of millihertz by an easily measurable amount. Okay? So that's a nice tool, is a clock drive.